So, next and last in the session, we're going to hear from Jeyhun, and he's going to tell us about a system called AStream that he built that allows you to combine multiple shared queries, shared stream query processing.
So, hi everyone. I'll present our recent work on AStream, and it's about ad hoc shared stream processing. Imagine online game scenarios. So, for example, PUBG is one representative example for some such scenarios. In those games, we have ad streams. Some ads are shown to the players regularly. And we have also purchaser stream. Players buy several costumes or buy let's say some points with spending some money. And there are many users, and the query throughput and data throughput are really high. Just only considering those two streams, ads and purchases streams, there might be a lot of ad hoc stream queries. How? Let's say a finance team at some point initiates query one, to analyze users which reside in Germany and spend more than 50 euros for purchase. And after some time, the team decides, okay, we're done, we don't need any more because the data we got is enough for us, and stops the query. And then query 2 is initiated by, let's say, psychology team, and this query is long-running query, it's never-ending. And after some time, the query 3 is initiated by marketing team because they have some new ad and they want to see how it will react on pro-level users. So, as we can see, there might be a lot of ad hoc users, especially join queries with different selection predicates. And the problem is that current stream processing engines lack an efficient processing of ad hoc stream query processing, stream queries. And also we have, as you can see, we have different selection predicates. And those selection predicates are not only just binary operators such as equality, they can be also defined with user-defined functions. We have to also make sure the consistency and the performance is also another problem. So we propose AStream, and we build our solution based on 3 main requirements. The first requirement is integration. So basically our solution or any ad hoc stream processing layer should be a composable layer over an existing stream processing engine. In this way, we avoid building a new streaming system, and we get benefit of large code base and various features such as fault tolerance, event time processing, distributed computing, and etc. The next requirement is consistency. So basically, removing and adding ad hoc stream queries must be performed in a consistent way. And of course, we have to also ensure the exactly one semantics and correctness of results. And another important point is the performance. So the current streaming engines minimize the latency and maximize the data throughput. But if for ad hoc stream processing engines, in addition to those requirements, we also have to maximize the query throughput, stream query throughput. And the system must share the resources and computation in order to enable the high performance. So this is the overall architecture of our solution. So basically, first, we have a shared session component which listens to user requests. And user requests are query stop or query create request. And it periodically generates a change log, the triangle in the figure. This change log then is propagated throughout the whole streaming topology. First from the shared selection instances, then to the shared join instance. And basically, at the end, it comes to the router instance, which propagates the tuples to output channels. So first, I'll explain shared selection instance, what's happening there, and also data model. And then I'll explain the shared join instances and how we compute in an incremental manner. So assume that at time 1, we create query 1 and query 2. Plus sign means query creation. And in shared selection instances, basically each tuple is appended a bitmap. And this bitmap we call as query set. And each bit in this bitmap shows if the tuple belongs, meaning if the tuple matches the selection predicate of a particular query. For example, tuple 4 matches the selection predicates of query 1 and query 2. Tuple 1 matches the selection predicate of only query 1. And assume that at time 2, query 2 is stopped and new query is submitted or created. Any operation among different tuples have to be consistent. Whether the tuple is created at time 2 or at time 1, the operation have to be consistent. And therefore, the query sets or the bitmaps the tuples has also have to be generated in a consistent manner. So because query 2 is deleted, one way to make those bitmaps consistent is just to set the second bit to 0 here, because query 2 is gone, and append the new bit for query 3. And this is one naive approach, and as you might already seen that this will lead to sparse query sets if we have very fluctuating query workloads. And what we propose is that when there are query changes, new query submissions and query deletions, we generate a change log. This change log contains metadata information about the new queries or deleted queries and a specific bitmap. This bitmap shows that which query changed and which query didn't change. For example, 1 means that query 1 didn't change, everything is there. And 0 means that query 2 either stopped and replaced with another query. And in both cases, it's changed. And all the query sets of the tuples after this change log follows the similar pattern. We don't change anything. So now let's go to the shared join, how we do the shared join. It's obvious that we do the window join. So our join operator also extends the windowing capabilities. And basically, having many queries and different window sizes and window types, such as time-based or session-based windows, we divide the windows into non-overlapping pieces, and we call them slices. For example, these are the windows we showed with yellow boxes, and the blue boxes are slices. And our shared join adopts an incremental computing technique. For example, if we want to join stream A and stream B, first, here, for example, the query 2 is ended. And basically, we have to join slice 2 from A and slice 2 from B. And basically, the two slices are joined and done. And here, for example, the query 1 is ended. So we have to join slice 1, slice 2, and slice 3 from both streams. And take a note that because we already joined slice 2 and slice 2 from A and B, we keep it as intermediate result and integrate the result to the next iteration. And basically, we remove the slices which are not used anymore. For example, here, slice 1 is not used, so we remove. And in that manner, the rest of the example follows the similar pattern. Okay, so one more thing. So, okay, we talked about the shared join, but how the join operation happens between slice. For example, how we do this join of slice 2 with slice 2 from A and B. So main intuition is that we group tuples inside slices based on their query set IDs. For example, if we want to join slice 1 and slice 2, and yellow group means that tuple 1 and tuple 2 belongs to, they both have query set 1, 0, which means that they both belong to query 1 selection predicate, they match query 1 selection predicate, and they don't match the query 2 selection predicate. And basically, if we want to join those groups, we have to make sure that those two groups at least share one query. How we can check that? Just by bitwise AND. If we bitwise AND those two groups, 1, 0 and 1, 0, which is 1 and greater than 0, and it means that they share some query, so we join them. We join tuple 1, tuple 2 with another tuples. But then assume that we have a change log between those slices, which means that, for example, query 1 is changed and query 2 didn't change. And then to make those two slices, we also add the bitmap of this change log to check that if they share at least one query. And as you can see, if we bitwise AND all those three, it gives a 0, for example. And this enables us to filter more redundant computation while joining different slices. Okay, so let's talk a little bit about the implementation details. So we design our system to be a composable layer over any stream processing engine. And we discuss in the paper how it's possible to integrate it with Apache Spark and also Apache Storm and Trill. And also our solution supports aggregation query sharing, although the semantics of the aggregation is a little bit different than join, not little bit, but different. And we support also various kinds of optimizations, which I talked about already, incremental query processing, and we eliminate redundant data copy and shuffling, and also we have dynamic slice structure, which enables us to adapt to different workloads, changing workloads. Also, our solution supports exactly one semantics, and all of the AStream components are deterministic, which means that even under failures, they will produce exactly the same results. So experiments. We perform experiments with 4 and 8 node cluster setups. We compare our solution with original Flink, and we have 2 workload scenarios. In the first workload scenario, basically, it's more or less a stable scenario. The query throughput increases after some time and stays stable. And the number of queries here are more than the workload scenario 2. But in workload scenario 2, the query throughput fluctuates, increases, decreases, increases, decreases over the time. And this is our benchmarking framework. Basically, our driver generates data tuples and user requests, which are query create or query delete requests, and they are stored in the queue. And the system under test will pull them from the queue and serve. The longer the tuple or the user request will stay in the queue, the higher its latency will be. So this graph shows the overall throughput in terms of million tuples per second. And overall throughput, we mean the sum of all throughputs, sum of the throughputs of all queries. And basically, and the legends show that, okay, for example, this legend show 10 queries per second up to 60 query parallelism, 100 queries per second up to 1,000 query parallelism. As we can see, with single query workloads, our solution has a cost overhead. But beginning from the 2 queries, our solution outperforms Flink. And interestingly, Flink cannot sustain the ad hoc workloads. And the reason is that as we submitted, for example, 1 query per second up to 20 queries, basically the deployment latency for Flink increased gradually. And so the sum of those deployment latency was more than 900 seconds, which is a really bottleneck. And this figure shows the overall data throughput for workload scenario 2. And as you can see that the throughput is less than the workload scenario 1, the one for workload scenario 1. And the reason is that by definition in workload scenario 2, we have less queries, but those queries are more dynamic and more fluctuating. And this leads us to better event time latency. And the reason is that we have many short-running queries, and our system is able to use this and optimize the bitmap size to be very small. And this overall leads us to a better performance. And in conclusion, we propose AStream, which is the first distributed ad hoc stream processing engine. And we show in the paper that current state-of-the-art stream processing engines cannot perform ad hoc queries. And not only the data throughput or latency, but also the query deployment latency and query throughput is a bottleneck for such systems. And our system supports majority of stream use cases, such as window joins, window aggregations, and combinations of them. And basically, we ensure ease of integration, correctness, and consistency, and high performance. And currently, we are working on extension of AStream to enhance the ad hoc and dynamicity in various of aspects. And thank you all for listening, and I am open for your questions.
Okay, do we have some questions? Over here.
So, thanks for the presentation, Jeyhun. Do you basically support one, let's say, specific query shape, let's call it?
Yeah.
I mean, what if you have 3 joins, one after the other?
So basically, join queries have to have the same join predicate. If you have multiple the queries with multiple predicates, then we can share them separately.
Okay, so how do you determine what part of the query can be shared so that you know basically how to match them?
Basically, if the sources are same and if the predicate is same, and we can share any join predicate is same, then basically we can share this pattern with any selection predicates.
Okay, so basically the queries have to be extremely similar for you to be able to join them all together.
Yeah, basically the sources have to be similar. But if they are not, basically we can group them into similar groups.
Okay.
Do you use something like a query optimizer to create logical, logical equivalents of subsets of the query so that you can try to match those?
Yes.
Okay. Yeah. Do we have any more questions? All right, then I'd like to thank all of our speakers today and thanks for the session.